constituent Hilbert spaces. Tensor product is key. That gives you entanglement. That allows for it. Now, 0 through 2 are only math. There's no connection with physics. We just shuffle symbols. Connection starts here, and 3 is okay. At least I don't see any problem with it. It's very hard to implement. Non-demolition measurements are exceedingly difficult to carry out, but conceptually it's useful and it's there. 4 and 5 come always in blue, especially 4. Question?
Isn't 3 in a way assuming 4 in the sense that you are measuring in an orthonormal, orthogonal basis at least?
So I'm going to get there basically as the next transparency. You are right. That it anticipates 4, right? But it doesn't give you the whole thing. So, you know, people who came up with quantum mechanics realized there was a problem. 4 and 5 clash with 0 through 3, and so they came up with interpretations. They were not always very convincing, the interpretations. Copenhagen was the word of the prophet, so to say, until Everett came around, and then Everett challenged it, and we will not rely on interpretations. We will not really talk about interpretations. If we want to somehow understand any of this, either Bohr's view or Everett's view, we somehow still need to understand where do preferred states come from. And so that's our goal. Now, I just explained to you they come from decoherence, right? I mean, pointer states and so on. So why don't we just go ahead and run with it? Well, here is my problem. Decoherence, and I'm not going to go through all of this again, depends on Born's rule. The moment you trace, you average. Averaging involves Born's rule. So we cannot use Born's rule if we want to do things in a way which would really explain how the postulates which are controversial, which have to do with measurements, come about. So all of this nice stuff about states commuting with interaction and so on should be questioned, and you know, the big thing that we need is that we need maths. We need somehow to know what things can happen. So let's see what we can do about it. So our plan for the remaining 25 minutes is to accept the top of the list, the stuff in yellow, Hilbert space, unitarity, repeatability, and tensor products, and see how much of 4 and 5 can we deduce from 0 to 3. So plan, why the measurement outcomes are limited to orthogonal subset of all the possible states in the Hilbert space, as in the collapse postulate. And why does Born's rule yield probabilities? And we have our hands tied. We cannot use Born's rule in deriving Born's rule. Right, so we need to do it somehow differently. Interestingly enough, orthogonality of measurement outcomes can be deduced reasonably quickly, just from the subset of postulates that I like, that we like. So let me show you how. We consider two states, U and V of the system, which are being measured by an apparatus. Apparatus is also quantum, and it starts in a state A0. Right? This transition is going to be unitary. And the measurement is going to mean that I have a state U and that state influences the state of the apparatus. So U evolves into U, AU, and V evolves into V, AV. I assume the repeatability, which means that the same state appears, of the system appears on both sides of this. If it's here, that means I could bring another copy of the apparatus and I would get the same result. So repeatability would be satisfied. So, turns out this is essentially what we need. If we have that, because the transition was unitary, what's on the left-hand side of the two processes and on the right-hand side of the arrows, scalar products of this and scalar products of this have to be equal. This is what unitarity means. Question?
I don't understand the notation. Do you mean that U tensor product with A naught? Is there a tensor product implied in there? Okay.
Yeah, sorry. That's right. Yeah, I'm going to do that throughout. So.
Okay.
Yes. Insert. Okay. So, if you have this, and if this was unitary, then you can write down scalar products of left-hand sides and right-hand sides. Right? This is an obvious equation. Now, if you have that equation, you see there is a common factor U scalar product with D on both sides. Temptation is to simplify the equation. So let's simplify the equation. So now I get AU, AV is equal A0, A0, which is 1, right? Because it's a product of the state with itself. So this means that we have just proved that measurement is impossible, because if AU, AV is equal 1, that means AU is equal to AV, that means that measurement didn't happen. The states of the apparatus have no imprint of the state of the system whatsoever. So can we just prove that our axioms are completely inconsistent? Well, not quite. Our problem was that we did the division. There is a case where you cannot do the division, which is exactly the case we are looking for. When the scalar product is 0, you get orthogonality. So indeed, repeatability leads you, along with unitarity, to orthogonality. Gives you the key part of the collapse axiom. Any questions? There was algebra in colloquia. One doesn't do algebra in colloquia. Fire away. Okay, so now we have orthogonal basis. Now we've proved why observables which are repeatably measurable are Hermitian. It implies restriction to orthogonal states. It hints at discreteness. Right? If you impose repeatability, you're not going to be able to measure a state and find out what it is. Repeatability is going to restrict you to a set of outcomes. So sort of hints at collapse. There's no real collapse, right? Unitarity. You didn't eliminate anything. Consequences and extensions. Derivation of quantum jumps. T2 collapse postulate from just the innocent axioms. 0 through 3. Implies that observables are Hermitian. Proof is similar to no cloning. If you don't know what proof of no cloning is like, don't worry about it. It can be extended when the apparatus of the environment is initially in a mixed state. Now this is really important. As I know, and as you may know, and as my experimental colleagues emphasize, making non-demolition measurements, measurements do not destroy the measurement outcome, is exceedingly difficult, very expensive, and always approximate. So at the microscopic level, we generally do horrible things to systems we measure. Photons are almost always absorbed in course of measurement. So we don't really need repeatability there. Where we do need repeatability is at the macroscopic level. We'd be very disappointed if macroscopic things, records in our computers or on our pages, got destroyed each time we looked. So this is really the level at which repeatability matters. Interestingly, you can extend this, there is more math involved, so I'm not going to go through it, to mixed decohering systems. So you can look at macroscopic objects, you can ask a question not about the microscopic state of what's there, it's enough to require repeatability of copies. Right? And so microscopic state is going to change, apparata and so on are plugged into walls, interact with the air and so on. Yet you will always see that the outcome was 17, for example. Predictability, which is extension of repeatability, is key to the proof. And information transfer need not be due to deliberate measurement. Any information transfer is going to do it. In a way, we have a sort of Born rule-free derivation of preferred set of states. And it really is Born rule-free. If you remember previous transparency, all that mattered is whether the scalar product was or was not zero. We did not invoke probabilities at any stage. Right? So we had a completely Born rule-free derivation of preferred sets of states. Okay, I'm going to switch gears again. Any questions at this point? You're convinced? Good. So we are back. So now, since we have states, we have distinguishable events. If we have distinguishable events, we can ask about their probabilities. So we go back to our plan, and we are done with a set of preferred states. Now we can ask about their probabilities. So we go to next part, which is why Born's rule yields probabilities. Before I get there, do a little bit of historical aside. So the paper of Max Born appeared in 1926. And this is a copy from the translation. And there is a footnote right on page 1. By the way, he was considering collisions. Electrons were hitting nuclear atoms. And he was interested of relating the wave function that describes electrons to the outcomes of measurements. I mean, the obvious question. And page 1 has a footnote. This report was originally intended for Die Naturwissenschaften, which was like a good journal, like Nature. But it could not be accepted there for lack of space. Nobel Prize, 25 years later. So if your paper gets rejected, don't despair. There's hope. You go to the next page. That's where the relation between the probabilities and amplitudes appears. And here's a sentence. If one translates this result into terms of particles, only one interpretation is possible. Psi, which is the amplitude, gives the probability for the electron arriving, etc., etc., etc. Now wait a second. Amplitude? Oh, but there is another footnote. Addition and proof. More careful consideration shows That's the probability is proportional to the square of the quantity side. Do your proof skill, please. Okay, so probability. Most of the time, we think of probability in terms of what is known as a relative frequency interpretation. You count number of things that happen. And so the statistical view is, I think, most familiar. This is not the original view of probabilities. Original view of probabilities has to do with symmetries. And I'm going to come back to that, right? It goes back to French aristocrats who played cards and other games of chance, were not very good at betting. And so they engaged French mathematicians who were very good at thinking about things to tell them how to bet. So the first book on probability that codified this view is due to Laplace. And there are other people